Motion of charge in a magnetic field, Part 1. Cancer is surely not a pleasant term to hear. It's a life-threatening disease which brings in challenging times for patients. However, with the advancement in technology, the diagnostic process in cancer treatments have increased the chances of survival compared to earlier times. Providing such a radiation therapy these days has become possible due to modern cyclotron technology. Cyclotrons employ magnetic fields to guide the charged particles in the cyclotron, which the electric field imparts energy to them. These charged particles produce radiations which are used for cancer therapy. In this topic, we shall understand how are the charged particles guided in a magnetic field. We know that the magnetic force vector Fb, which acts on a charge q moving with a velocity, vector v in a magnetic field vector b, is given as vector Fb equals q times vector v cross vector b. Using the cross product rule, its magnitude can be written as Fb equals qvb sine theta. Here, theta is the angle between velocity vector v and magnetic field vector b. Now let us examine the magnetic force acting on the charge particle for different values of theta. Equation 1 tells us that if a charge moves in the magnetic field with its velocity vector v parallel to vector b, that is theta equals 0 degrees. The magnetic force acting on the charge is 0. The same is true if vector v and vector b are anti-parallel. That is, theta equals 180 degrees. In both the cases, the motion of a charge is not influenced by the magnetic field. Now consider a freely moving positive charge q entering the magnetic field such that vector v is perpendicular to vector b. In this case, theta equals 90 degrees and hence the magnitude of the magnetic force is maximum and is Fb equals q times v times b. To find the direction of Fb on the positive charge, we use the right-hand rule of cross product of vectors. Orient your right hand in such a manner that your outstretched fingers point in the direction of velocity vector v, and when you bend them, they point in the direction of magnetic field vector b. Then your outstretched thumb will point in the direction of magnetic force vector Fb. It is this force that changes the path of the charge in the magnetic field. At point L, the force Fb is perpendicular to v. This force bends the trajectory of the charge and it reaches M. At this point, the force pulls the charge inward, bending its path further, and the charge reaches point N. The charge is acted upon by a constant centripetal magnetic force at every point of its trajectory. As the force is always perpendicular to its velocity, the displacement, that is, the work done by the magnetic force on the charge, is 0. In other words, the energy of the charge as well as its speed remain constant. Therefore, the magnetic force merely changes the direction of velocity of charge and not its magnitude. As a result, the charge performs a circular motion within the field. Since the charge is now held, we say that the magnetic field has trapped the charged particles. The above fact is true for the negative charge also. But the direction of the magnetic force acting on it is opposite to that given by the thumb in the right-hand rule. For a circular motion, the centripetal force F equals m times v squared by r. Here, the centripetal force is provided by the magnetic force Fb. Hence, QVB equals m times v squared by r. Therefore, the radius r of its circular orbit is r equals m times v by q times b. Summary. Modern cyclotron technology plays a crucial role in radiation therapy. Cyclotrons use the magnetic and electric fields to increase the energy of charged particles and produce radiation, which is used for cancer treatment. The magnetic force vector Fb, which acts on a charge q moving with a velocity vector v in a magnetic field vector b, is given as vector Fb equals q times vector v cross vector b. In cases when theta equals 0 degrees and theta equals 180 degrees, the magnetic force acting on the charge is 0. In the case of theta equals 90 degrees, the magnetic force is the maximum. Under the influence of this force, the charge performs a circular motion within the magnetic field. The radius of the circular orbit is given by r equals m times v by q times b.